All right. Hi, my name is Howard. I'm a graduate student at UC Berkeley. Today I'm going to talk about DIZK. This is a distributed zero-knowledge proof system, and this is joint work done with Wenting, Alessandro, Raluca, and Jan. So to begin, what is a zero-knowledge proof? Well, a zero-knowledge proof involves two parties, a prover and a verifier, and both know of a public function f and some claimed output y. The prover says, hey, I know some secret input x such that f of x is equal to y. And the verifier will challenge the prover and they play this interactive game, after which a prover will convince the verifier that they know this claim. Now, one particular type of zero-knowledge proof that has gained significant attention is that of ZK snarks. And a ZK snark is a zero-knowledge proof that has a few additional guarantees. First off, it is non-interactive, meaning the prover only needs to provide a proof to convince the verifier that they know the private input x. But in addition, it is also succinct, meaning that the proof is small in size and the verification time is fast. One particular type of ZK snark that we're going to look at today is a pre-processing ZK snark. And this is one where you have a setup that takes as input a public function f and produces two outputs, a proving key and a verification key. Note that the proving key here is significantly larger than the verification key. And overall, ZK snarks have many interesting applications, two of which we'll discuss today. So the first application that we're going to look at is peer-to-peer payments. Suppose Alice wants to pay Bob $1. She may use something like a blockchain to facilitate this payment. But this would certainly reveal that she's the sender, that Bob's the receiver, and that the payment amount is for $1. Instead, Alice could encrypt the contents of the payment, attaching a ZK snark proof attesting to the validity of this payment. This is actually a protocol called Zerocash, which is manifested in industry as Zcash. Let's look at a second application. So suppose you wanted to use smart contracts to run a publicly verifiable computation. Well, today, invoking a smart contract requires validators to rerun the computation. And a more scalable approach is for the caller to run the computation off-chain, sending the result along with a proof, and attesting to the validity of the result. Then the validators would only need to check the proof. And we have already established here that the proof itself is quite cheap. So first off, these are only two applications of zero-knowledge proofs, and don't be offended if your favorite application wasn't presented here. These two applications were chosen specifically to motivate our problem, which I'm now going to address. So we have some good news and some bad news. If we look at the circuit sizes of the applications that we just discussed, well, in the case of a private payment, we're looking at something that is approximately 1 million gates. And this is actually pretty good. It's practical, and this is something that can be used in current ZK snark implementations. However, if we look at a typical smart contract execution, we find that the size is approximately 100 million gates. And if we look at even larger smart contract executions, we find ourselves using billions of gates. Unfortunately, current monolithic ZK snark implementations run out of memory at approximately 10 million gates. And this makes these applications just out of reach from current techniques. So we asked ourselves, what would be a stepping stone for enabling applications such as this? And so we designed DIZK. DIZK is a zero-knowledge proof system that is, one, distributed, meaning it enables the execution of a ZK snark setup and prover across a compute cluster. Two, it is scalable, meaning that it reaches heretofore unreachable circuit sizes, up to billions of gates. And the pattern that we see here is that as we double the number of machines, we can support approximately twice the number of circuits. And lastly, it is parallel, meaning that we can speed up the time it takes to generate a proof. And the pattern that we see here is that as we double the number of machines, the proof generation itself runs at approximately twice as fast. So how did we do this? Well, the approach that we took was we used a monolithic ZK snark, namely one by Jens Groth from 2016, and we distributed it on a cluster of machines. Now, this approach appears quite simple. However, it turns out there were a lot of challenges to distributing this protocol. We chose Groth16, for example, specifically because it's highly efficient and currently offers the smallest ZK-SNARK proof size. And in general, we had to tailor our architecture at every level to ensure that our protocol could adequately demonstrate scalability and parallelism. Let me walk you through some of the challenges we faced now. So take this diagram of a ZK-SNARK protocol, and I want to point out that the verifier here is extremely small and cheap to run. Therefore, we're going to turn our attention to the setup and the prover. At first glance, we'll want to spin up a cluster of machines and run the setup and prover on it. Next, we'll want to use a distributed data structure to represent our public function f, our proving key, which we said was large, and our secret input. This looks all right. However, it's not. There are several challenges that arise with this current setup. First, we're multiplying polynomials of degree that are now in the billions. Two, we're representing these polynomials as terabit-sized arrays. Third, we're accessing large pools of shared memory in complex access patterns. And fourth, we're synchronizing shared state that incurs significant network delays. These are fundamental challenges that we need to overcome, and so we do so in the following way. For DIZK, our architecture looks like this. So we start with the setup. It turns out it's not enough to keep the subcomponents of the setup monolithic, and so we distribute the setup by implementing distributed algorithms for each of the subcomponents in the setup. The distributed setup then outputs a distributed proving key and a small verification key. Just as before, we distribute the prover by distributing the monolithic subcomponents of the prover. And lastly, the verifier will then check that the proof is valid. And again, we forego distributing this step as it is extremely cheap to run. For the sake of time today, I want to focus on one critical part of our system, and that's the distributed prover. You'll find detailed explanations for all of our techniques in the paper. And today I want to discuss one critical component in our system, that is the witness reduction. I will go over our thought process for distributing this guy, and also show you some of the few off-the-shelf approaches to computing the reduction, and lastly show you the tailored approach that we used to make the witness reduction itself both scalable and parallel. So to efficiently compute the ZK-SNARK proof, we need to reduce the circuit we started with into polynomial form. And namely, the equation that we are going to evaluate here is this one. If you haven't seen this equation before, this is an important equation introduced in GGPR 13 that defines a quadratic arithmetic program, and this has to do with arithmetization of circuits. If we zoom in on this equation, there are three terms that need to be efficiently represented and evaluated in order to perform the witness reduction. And also notice that these each have summations that are from 0 to n, and n here is going to be in the billions. So I will focus on how we can efficiently evaluate these summations. Note that the arithmetic operations outside of these three terms will make use of distributed FFTs, which I will leave to the paper. Now, zooming in on one of these terms, we see that there are two components, a matrix A and a vector Z. The matrix A represents one part of the input wires comprising our circuit, and the vector Z is a satisfying assignment to the circuit. You can think of it as a combination of the public inputs and the secret inputs. So we start by representing our matrix A as an n+1 by m matrix, and we'll represent our vector Z as an n+1 vector. And for a strawman approach, to evaluate the sums, what we need to do first is join the elements by their index here, which is I. We may partition our matrix A row-wise, and our vector Z element-wise. And next, we'll join our partition row-wise. So, A0 goes with Z0, A1 goes with Z1, and all the way down to AN with Zn. And this generates a join table that looks like this. It appears quite uniform in cost, with each entry now independent of all other entries. However, it turns out this isn't the case, and let's see why. So because of the nature of our circuit representation, our matrix is what we call almost sparse. This means that most rows and columns are sparse. However, there will always be a handful that are dense. If we partitioned our matrix column-wise for the cluster to compute, the second column in this case would be slow and what we would call a straggler. This causes all the other machines to wait on it to finish its task. So if we partition our matrix row-wise, again, we actually run into the same problem. And as you'll see here with the first row as our straggler, causing all other machines to wait on it to finish its task. So we studied some off-the-shelf approaches, and the goal here is to address the problem of data skew, and we benchmark them across varying circuit sizes and number of machines to determine their feasibility. The approach that's taken by these off-the-shelf approaches is to replicate and partition the data. So the first approach that we looked at was block join. Now, block join is a common technique to address data skew, and what it does is replicate each of the entries in one distributed data set across every machine. The hope is that when joining with the other distributed data set, the partitions will be more evenly spread across the machines. And what we end up with is a join table that looks something like this. Now, at first glance, this table looks quite large, and indeed it is. Block join has performed actually n+1 times the number of partition replications. And recall that n+1 here is in the billions. So every partition is dense, and so we could say that, hey, maybe the computation is uniform. That's actually true, but the table is also now huge and impractical to compute. So this doesn't work for our system. And so we turned to other off-the-shelf approaches and looked at them as well. Namely, one is a system approach called skew join. And with skew join, we benchmarked this, and we see that skew join basically is trying to take a more fine-grained approach. What it does is first compute usage statistics, and only then replicate frequently used entries for every machine. This sounds more reasonable, and indeed in most cases it really is. However, for our system, it turns out this provides us minimal advantage. And let's see why. So if our matrix A is partitioned row-wise, and we perform a skew join operation with vector Z, we see that each partition only needs access to one unique element from the vector Z. In this case, it turns out actually that skew join is functionally equivalent to that strawman approach we saw earlier. And if our matrix A is now partitioned column-wise, and we perform a skew join with vector Z, we see that each partition now needs access to every unique element from the vector Z. And in this case, no matter how we organize our data here, the off-the-shelf approach will cause unnecessary replications that blow up our memory cost requirements, making it impossible to scale the system. And if you observe here, this is actually equivalent to block join from earlier. So, in fact, we found that the foregoing skew join approach does not scale beyond 50 million constraints, even on 128 machines. And until then, it's actually twice as slow as our tailored approach, which I will now describe. So we designed and implemented a tailored approach to evaluate our witness reduction. And the approach we took was to isolate and transform the data so that the computation is distributed evenly. Let me show you at a high level how we do this. So we start with an almost sparse matrix A from before and perform a pre-processing step whereby we compute the density count for each partition. Now, to perform the join operation between matrix A and vector Z, we perform what we call a hybrid join, which replicates only a handful of unique elements from vector Z. As we said, our matrix A is almost sparse. And so in this case, we need to split our dense vector into sparse partitions. And from there, we will perform our hybrid join with all the individual elements connected to their respective partitions here. Notice that each partition has just one non-zero computation. In this case, that means that we just have one dense computation to perform in each of these partitions. And as our replication factor was minimal, because our approach itself was able to preserve the almost sparse structural representation of matrix A, we find that this enables us to join our data to compute the summations from before without stragglers. In practice, for the same number of machines, we find that our tailored approach now enables us to reach billions of gates, where off-the-shelf approaches kept us in the millions of gates. And so, along with the other distributed subcomponents we describe in this paper, we're able to architect a zero-knowledge proof system that is scalable and parallel. So we implemented the system, and we used a cluster compute framework, Apache Spark. Our system is written in Java with approximately 10,000 lines of code. And we ran our experiments on Amazon EC2 and using R3 8x large instances. Our evaluations show us some interesting patterns and properties, which I will now present. First, we evaluated our system on the largest supported circuit size. So when we profiled libsnark in our environment, we found that it reaches approximately 4 million gates. And when we profiled DIZK across different numbers of machines for the same environment, we found that we were able to reach approximately 2 billion gates with 256 machines. The pattern that we see here is that as we double the number of machines, we're able to support approximately twice the circuit size. This then led us to ask, could we compute up to these large circuit sizes in a time-efficient manner? And so we have here two graphs that demonstrate scalability. So on the left graph, we have the distributed setup, and on the right graph, we have the distributed prover. Note that this is a log-log graph, and if we follow the line for 256 machines, we see that the slope is actually approximately 1. And so the pattern that we see is that as we double the circuit size, we're able to generate our proof and run our setup at approximately twice the time. This is a good demonstration that our system here is indeed scalable. And here, again, we plot the same data, but now we show the machines on the x-axis and plot the circuit size. On the left, again, you see the distributed setup, and on the right, you see the distributed prover. And if we follow this particular line here at 2 to the 26, the pattern that we see here is that as we double the number of machines, we're able to run our proof generation at approximately twice as fast. So in conclusion, we found that prior ZK snarks support maximum circuit sizes of approximately millions of gates at an amortized cost per gate of about 1 millisecond. And we find with our techniques that DIZK is able to support maximum circuit sizes in the billions of gates at an amortized cost per gate of 10 microseconds. The full paper is available on Crypto ePrint, and I'm proud to say that we have released DIZK as an open source library on GitHub. You can find it by going to dizk.org. And we've put a lot of hard work into making this library available to the public with a convenient profiling infrastructure so that you can replicate our results as well as build new and interesting applications using DIZK. Lastly, I would like to leave you with two open questions. And the first is, with regards to even larger circuits, what techniques will get us to trillions of gates, if any? With our current techniques, we would need approximately 100,000 machines in the best case scenario, and this in practice is just too many. The second question is with regards to other succinct zero-knowledge proofs. So how efficiently can other succinct zero-knowledge proofs be distributed? Our techniques seem like an excellent starting point for things like SARCs and bulletproofs, and etc. And with that, I'd like to conclude, and thank you for your attention.